Hello everyone, thank you for having me to the conference. My name is Dr. Cheng. I am going to speak to you on the topics on intelligent audio systems. I am from Newcastle University in Singapore. To begin, let me give the research interests that I'm currently working. My research interests are in intelligent system design of complex systems in uncertain environments involving predictive analytics such as data mining, predictive modeling, and machine learning. I've obtained a few research projects in the area of AI systems for energy storage, smart manufacturing, intelligent water leakage warning systems, battery power systems for underwater robotics vehicles, noise vibration control, as well as psychoacoustics parameters in hard disk drive. So my research area, as I mentioned, is in intelligent system design involving different domains such as battery acoustic systems, electric vehicles, and water distribution systems. Intelligent systems, problems, needs, and industry relevance. Intelligent systems rely heavily on context awareness. So what is context awareness? It's the ability of a systems or the system components to gather information about its environments at any given time and adapt behaviors accordingly. And environments or the information about its environments involving acoustics, visuals such as images as well. So being able to detect and classify sound and event from surrounding is an important aspect of context awareness. So to give you a background of the applications of sound classifications, sound classification is one of the most widely used applications in audio deep learning. It involves learning to classify sound and to predict the category of the sound. This type of problem can be applied to many practical scenarios. For example, classifying music clips to identify the genres of the music, acoustic scenes classification, and sound event detections. It serves many important applications, for example, that you can see on top of this slide, to capture the acoustic characteristic of the real-world rooms using devices such as handphone and use the capture characteristics to generate similar sound source with virtual model. Alright, so once you can capture something using the microphone, you can duplicate it as those that someone is sitting in front of you. Another applications is AI is critically in the care settings could reduce the nurse workload to allow them to spend time on more critical tasks, and it could also augment human decision making for offering low cost and high capacity intelligent data processing. So this is a kind of scenario that in the hospitals, alright, which we can actually monitor the performance of the patients. Okay, so how pervasive sensing technologies and AI can be used for monitoring patients and their environments in the ICUs. So you can see that the wearable accelerometer sensors, light sensor, sound sensor, and high resolution cameras to capture data on patients and their environments in the ICU or in any rooms. So these are some of the architecture that you can build on. Like for example, you gather all the informations and process using the sensors, and then you can actually have some pervasive patient informations, and then you can actually subsequent decisions on how the patient cover. First, let's look at the sound events detections. Sound event detection refers to a system that is capable of detecting the type of audio event present in the audio clips, such as audio taggings, returning the onset and offset of the identified acoustic events, and SED can be categorized as the monophonics or polyphonic systems. So what is monophonics and the polyphonics SED? As you can see that when we have the input sound, we go through a sound event detection systems. You can identify the onset means that the start and the offset or the end of a certain speech, or the dishes, or is it coming from the vacuum cleaners. So for polyphonic SED, meaning that there's overlapping sound scenarios such as the dog and the speech. So where dog is barking, someone is talking. So there's overlappings. However, for monophonic SED, there's a very clear-cut separations between the dog and followed by there's alarm and then so on and so forth. Alright, there's no overlapping sound. Polyphonic SED system is more appropriate in the real life application because it resembles what is actually happens, such as when I'm giving a speech, probably in my background there's someone is talking. Alright, so it's more likely to contain multiple sound events. That's what we always talk about monophonic SED. So another scenario that I want to give you is the sound event detections. For example, for phone ringings, going through the SED sound event detections, you can detect what is the begin and the end of this phone ringing. So this is what I call very clear cut. So this is called the very strong label data. But in the event of, let's say, phone ringing, yes, you can know is for strong label, as I mentioned, it begin let's say 0.36 second and end 0.78 second, and we can classify this as phone ringing. But for weak label, meaning that it can be phone ringing, the event tag are known for certainty, yes, it's a phone ringing, but this can compromise the solution because under this weak label data, there might be some other background noise that can influence. So sound event detections is very useful. Why? Because it's not affected by degree of illumination, meaning that for the imaging can be affected by this. Some event can only be detected by sound because some event can be detected by sound. So sound can capture the immediate attention of the individuals. And audio clip require lesser computation resource as compared to image or videos. So these are some of the advantage of using sound event detections. So what are the challenges for sound event detections? So sound developments may require a large amount of strongly labeled data, okay, where the event tag, we know that is the phone ringing, and their corresponding onset, offset are known for certainty. Okay, onset means the start, offset means the end. So, but that means that it's difficult to and time consuming to collect, and the accuracy onset, offset annotations is ambiguous due to the fade-in and the fade-out effect. So such dataset is usually limited to minutes or even in few hours in total. So I just want to give you some demo. So this is music being classified. So the telephone is ringing now and it's being classified. So this sound classification system apply to audio tagging system to build a sound event detection. So we actually do this audio tagging, meaning that we can actually find out whether is it what type of sound is currently on the background. And the SED prediction is obtained by applying the audio tagging systems on consecutive 2-second segments. So let's move on to the acoustic scenes classifications. So this is another area of sound classifications. For acoustic scenes classification, as you can see that if you record the sound using different device and you go through the acoustic scenes classifications, you can classify whether the sound come from scenes such as petrol station, urban park, or public square, for example. So this is very good because, for example, in some application, you can try to adjust the smartphone ring volumes when the owner move from a very quiet acoustic environments into the noisier environment. So this is one of the very simple applications in the smartphone. But what are the challenges for acoustic scenes classifications? So it's also time consuming to collect for each scene. Dataset is usually limited to minutes or a few hours, as you can see from the SED as well. So thus the short audio segment provide less information and also making ASC difficult to predict or being used. Acoustic scenes can share very similar profile making and it's difficult to be classified. So ambient sound scenes typically comprise of multiple short events occurring on top of sound stationary backgrounds. So there's a lot of background noise that influence the sound. And the foreground background ambient sound scene separation is also quite challenging if you want to separate the background from the foreground sound. So just to move on to the acoustic scenes classification systems, and this is one of the examples that I want to illustrate after giving you a brief intro on the SED as well as ASC. So I will just talk about ASC. So the top performing systems in one of the very popular sound benchmark data set that we use is the detection and classifications of acoustic scenes event, in short DCASE challenge, and it consists of multiple models using the convolutional neural network CNN. So these are the most common methods being used. So instead of using the log mule spectrogram as features that we extract from the wave files, wavelet time scattering has been used. So the extracted features are quite insensitive to translation, rotation, and small deformations. So if you use a wavelet time scattering, and it also produces a more accurate classifier in dealing with variation in the ASC. We will start with the sound file. So we convert them into spectrogram and input to the CAM plus the linear classifier model and produce prediction about the class to which the sound belongs. The wavelet features are used for example classifier. Alright, so this wavelet feature will be only used in the example random subspace discriminant classifier. And this consists of basically the linear discriminant analysis, quadratic discriminant analysis, regularized linear discriminant analysis. So to reduce the overfitting of the data set in CNN, for this case where we use the log-mu spectrograms, a mix-up algorithm is used for the log-mu spectrogram features. Alright, so there's no mix-up being used for the wavelet scattering transform features. A multi-model late fusion is then used to fuse these two parts, the log-mu CNN as well as the wavelet example classifier. So it will provide a time frequency representation of audio to capture the spectro-temporal modulation patterns for identifying various acoustic scenes. Just look at the data sets that I mentioned before. It consists of 15 scenes, right, from bus, forest path to residential area to tram. So we are using the TUT acoustic scenes 2017, which is the part of the D case data set was used for this experiment. It consists of 10-second audio segments from these 50 acoustic scenes. So each acoustic scene has 312 segments. We are giving a total of 52 minutes, so meaning that 312 times 10, and then we change to minutes, so divide by 60. So you can see that the sound recordings were performed via different devices at 24-bit resolutions and 44 100 Hz sampling rate. So the microphone was worn during the recording. So the detail, you can look at these data sets and how we collect all these informations. So just to give you a sample view of how this data set, for example, the beach sound, and how this train will sound like. So the scalegram is the absolute value of the continuous wavelet transform, which called the CWT of the signal. So this is the signal of the beach for examples. So this is the scalegram and being transformed. So this scalegram will help to analyze the real-world signals with features occurring at different scales. So for example, signal with slowly varying event punctuated by the abrupt transients. So you give a better time localizations for short duration, high frequency events, and also a better frequency localization for low frequency, longer duration event. So this another scalegram that I've shown here for the train as well. For the sample data, you will see that this is the beach. You have a sample of the entire scalegram for this class called beach. And another data samples for the train, you will see that this is just a snapshot of all the scalegram being used for the train class. And as I mentioned, for the log-mu spectrogram, we are using the data augmentation, which is the common one that we use, is a mix-up. And I believe that you know what is a mix-up about, but here is basically a technique that literally mixing all the features and their corresponding labels. So this lambda is basically values that can be ranged from 0 to 1. So if the lambda equal to 1, precisely you are not doing any mix-up. So lambda will be from somewhere the 0 less than 1. Alright, so the xi and sj are the raw input vectors, and the yi and yj are the label encodings, meaning that label of the sound. So this convolution neural network CNN, so we are using for the log-mu spectrogram, we are using the CNN. So we have the batch normalizations, which is the common one, and the rectified linear unit ReNU are used. This ReNU will help to increase the non-linearity in the image, or for this case is basically when we talk about this image is our log-mu spectrograms. And the batch normalization learning is used as a regularization to prevent overfitting. So this helps to prevent the overfitting, and the activation function and BN are located before the combination layer to improve the acoustic classifications accuracies. And then you know that the max pooling layer come after the combination process. So this is pretty quite standard architecture, and then followed by feature max that includes the prominence features is obtained by output of these max pooling layers. So we know that the poolings, the average poolings reduce the activations by combining the non-maximum activations. And then we have a dropout layer of 50%, and it also help to reduce the overfittings. And the fully connected layer is compile the data to form output of the last second layers that use the softmax activation function to obtain the probability of input from these 15 classes, which is the part of the DK's 2017 dataset. And lastly, the last classification layer produce the final classification, whether is it come from the train, the park, the beach, and so on and so forth. And then not forgetting the wavelet scattering is one of the features that we extract from the wave file. So is basically involve the feature extraction using the wavelet scatterings, as I mentioned, and the parameters of this transform are the filter band using the 1D modeled wavelets. Resolution is Q1 is 1 and Q2 is 4. And the duration is 0.75 seconds of the averaging filters, or what is known as the invariant scale, is used for modulation structure durations, and the sampling frequency is 44,100 Hz. And the proposed example classifier includes the different discriminant analysis learners, as I mentioned, the LDA, QDA, and RDA, and also other predictor covariance treatments. The random subspace learning method is being used to increase the acoustics classification accuracy, and in this random subspace, the feature subspace are chosen randomly from the original feature space. And the final prediction of this individual classifier is then obtained through majority voting of this LDA, QDA, as well as RDA. So we use the majority voting approach. And then we remember we have to fuse the CNN and the classifier, which is the example classifier. So the fusion of CNN and the example classifier prediction result indicate the relative confidence of their predictions. So how we do that is we actually do a max fusions of the probability from the CNN as well as the probability of the example classifier. So here we run the experiment using our laptops, the Intel Core i7, 2.6 GHz 6-core and GeForce RTX 2060. And the configuration of the proposed model that I mentioned, we use the stochastic gradient descent with momentum optimizer with a learning rate of 0.05 seconds. And because of the limitation of laptops, I mean, you can always try to increase the mini batch of each training iteration. Here we set as 1 to 8. The momentum is 0.9, and the maximum number of epochs is 8, and the factor for L2 regularization is 0.005. The number of epochs for dropping the learning rate is 2, and the multiplicative factor applied to learning rate for each epoch is 0.2. So to show you the results and the discussion, we compare with the baseline model, meaning that the baseline model provided by the challenge, which is the DK's 2017. So this baseline model look like what you see on the left hand side. There's a input, there's a 2D combination layers, batch normalization, renews, activation, 2D max pooling, and dropout, and this considered as one CN layer. And then there's another one that is similar, just except the filter and the kernel size is different for the first part, and then followed by flattened or dense layers, and then followed by the output using the soft max activation, and followed by the final classification results. So that this is the baseline model that they use. So you can see that the baseline model, which they have an average of 61 classification accuracy. This is obtained by sum up all the classification accuracy of this individual class and divide by 15. And then for the CN itself, if you just use a CN just alone itself, you get 73.3. And if you use the example classification model by itself, we get 76.3. But if we combine them, fuse this model together using the max fusion, we get 79.4. Alright, so this is the confusion chart that you can see on the blue side, meaning that we want to have a higher If there's a higher one, you will see that it's highlighted by blue, and you have a dark color in red, meaning that this is not as good as what we want. So the example classifier has a higher acoustic accuracy than the CN, but when we compare with both of them, we find that the baseline model is still not as good as the individual as well as the fuse model. Alright, and then just take note that the fuse model SP around 18.4% higher accuracy as compared to the baseline model that is given by the challenge. And then if we compare with CN only, alright, you can see that the result of the scene like beach using ensemble classifier is 37.96%, is quite poor as compared to CN itself is 73.14%. But the fuse model managed to increase the acoustics classification accuracy to 50.92%. But conversely, when you look at the scene such as the park using the CN model, it's relatively low compared to ensemble classifier. The fuse model managed to increase it to 60.18%. So you can see that this fusing of these two models helps to leverage or try to balance the performance of each of these class. The confusion charge of CN ensemble classification and the fuse model are shown as you can see here. Alright, and the average acoustic classification accuracy of the fuse model as measured in the table just now is computed as 79.43%. So in conclusion, what I want to conclude is that this multi-model lake fusion systems consists of the log-mule spectrogram for the CN and the wavelet time scattering for the example of subspace discriminant classifier was proposed, and then you will find that we based on the data set from TUT acoustic since which is 2017, which is also the DK's 2017 data set, and it demonstrates that the fuse model give a good accuracies. For this case is 79.43%. So the proposed multi-model fuse lake fusion system SP actually 18.4% higher acoustic accuracy of the classification accuracy than the baseline model, despite relative low performance in some of the scenes such as the beach and the library. So nevertheless, the multi-model lake fusion system show a very good acoustic classification accuracy for most of the scene. So in summary, I could say that to achieve a very higher performance for this case like acoustic classification accuracy, in the literature most of them use example approach, meaning that you try to combine a few methods and fuse them together so that they can high accuracies in their performance. So with that, I just want to show you some of the related publications from 2019 and to present. For example, we have the neck that we propose for the sound event detections, published in IEEE Transaction of Audio Speech Language Processing, and also we have IEEE SS as well as some other publications in the conferences. And welcome collaborations. If you have any questions, you can ask me later. With that, thank you very much.